Today, we are unlocking one of the most dramatic, beautiful, and least understood secrets of the cosmos, the Roche limit, an invisible celestial boundary that turns entire moons into the glowing, iconic planetary rings that adorn the giant worlds of our solar system and beyond. For centuries, humans have stared upward in awe at Saturn's shimmering rings, marveling at their perfect symmetry and ethereal glow. Yet, for most of that time, we had no idea how they came to exist. We once thought they were solid bands of rock or ice, a permanent feature etched into the universe since the dawn of time, but the real story is far more violent, far more poetic, and far more revealing of the unyielding rules that govern every star, planet, and moon in existence. The Roche limit is not just a number or a physics formula, it is the line between life and death for a moon, the moment when a planet's gravitational might becomes too much to bear, and a once whole world is pulled apart into a celestial masterpiece. To understand the Roche limit, we must start with the force that binds the entire universe: gravity. Most of us think of gravity as a simple uniform pull, but in the vastness of space, gravity is not equal across any object. When a small body like a moon orbits close to a massive planet, the side of the moon facing the planet experiences a far stronger gravitational pull than the side facing away. This difference is called tidal force, and it is the engine behind the Roche limit. Imagine standing in space, with your feet pointed toward a giant planet. Your feet would feel a much stronger tug than your head, stretching your body like taffy, in a process scientists casually call spaghettification. On a planetary scale, this same gentle-sounding force becomes a wrecking ball. A moon holds itself together with its own gravity, a quiet cohesion that keeps rock, ice, and metal fused into a single sphere. But when that moon drifts too close, the planet tidal stretching becomes stronger than the moon's ability to hold itself together. That critical distance, where tidal force defeats self-gravity, is the Roche limit. Cross that line, and no moon, no matter how solid or rocky, can survive intact. The man who first uncovered this cosmic rule was Édouard Albert Roche, a French mathematician and astronomer born in 1820. In 1848, at just 28 years old, Roche became obsessed with a stubborn mystery. Why did Saturn have such distinct rings, while no other planet we knew of did? Why did the particles in those rings never clump back together to form a new moon? Working alone in his study at the University of Montpellier, Roche spent weeks crunching equations about gravity, orbital mechanics, and celestial cohesion. He calculated the exact distance at which a planet's tidal force would overcome a satellite's own gravity, proving mathematically that any moon moving within that boundary would be torn to shreds. He published his findings to a quiet audience, but his work would go on to redefine planetary science. Today, that critical distance bears his name, the Roche limit. For fluid, icy bodies, the Roche limit sits at roughly 2.44 times the radius of the parent planet, while denser, rocky moons can edge slightly closer before breaking apart. This simple calculation explained everything we had failed to grasp about planetary rings for centuries. Let us paint the full cinematic story of a moon's final moments. Hundreds of millions of years ago, a medium-sized icy moon orbited Saturn in peaceful stability, much like Enceladus or Mimas does today. But over time, orbital decay and tidal interactions slowly sapped the moon's energy, pulling it incrementally closer to the giant planet. For millions of years, the moon held strong its own gravity, just enough to resist Saturn's increasing tidal pull. Then it happened, the moon crossed the Roche limit. At first, the change was subtle. The once round moon began to stretch, bulging toward Saturn, and flattening at the poles, turning from a perfect sphere into an elongated oval. Cracks spread across its icy surface as the tidal force pried apart rock and ice. Then, the outer layers began to peel away huge chunks of ice, breaking free and spreading into a thin rotating disk. Over thousands of years, those chunks collided, shattered, and ground themselves into countless smaller pieces, from dust grains to boulders the size of mountains. The moon that once was ceased to exist. In its place, Saturn's iconic rings, a dazzling memorial to a world that was torn apart to create something infinitely more visible. NASA's Cassini mission, which orbited Saturn from 2004 to 2017, confirmed this story with stunning clarity. Cassini's data revealed that Saturn's rings are surprisingly young, just 10 to 400 million years old, younger than the dinosaurs. They are not ancient leftovers from the solar system's birth. They are the recycled remains of a moon that's met its end at the Roche limit. The Roche limit does not only shape Saturn, it rules every ringed world in our solar system. Jupiter, the largest planet, has faint, dusty rings formed when small moons wandered inside the Roche limit and disintegrated. Uranus and Neptune, the ice giants, host narrow dark rings made of rocky debris, also forged by tidal destruction. Even beyond our solar system, the James Webb Space Telescope has spotted ring systems around exoplanets, all confined neatly within their planet's Roche limit. One of the most dramatic examples in modern history is Comet Shoemaker-Levy 9. In 1992, this comet passed too close to Jupiter, crossed the Roche limit, and was torn into more than 20 distinct fragments. 2 years later, those fragments slammed into Jupiter's atmosphere in a series of explosions visible across the globe, a vivid demonstration of the Roche limit's unforgiving power. Looking to the future, Mars' moon, Phobos, is slowly spiraling inward, doomed to cross the Roche limit in about 50 million years. When that day comes, Phobos will be torn apart, draping Mars in a thin, beautiful ring that will last for millions of years. What makes the Roche limit so profound is that it embodies the universe's greatest paradox: destruction creates beauty. The Roche limit is not a force of chaos. It is a force of order, a universal rule that shapes how planetary systems evolve, how moons live and die, and how the most stunning sights in space come to be. It teaches us that nothing in the cosmos is permanent, that even solid worlds can be transformed, and that the universe's most breathtaking features are often born from events that sound catastrophic. NASA's ongoing research into the Roche limit helps us map the life cycles of moons, predict the fates of celestial bodies, and understand how planetary rings form and fade over time. Every time we look at Saturn's rings, we are not just seeing ice and dust, we are seeing the ghost of a moon, torn apart by tidal gravity, to create a work of cosmic art. The Roche limit is a reminder that the universe is not a silent, static place. It is dynamic, violent, gentle, and creative all at once. It is governed by rules that we are only beginning to fully understand, rules written in gravity and motion, in destruction and rebirth. From the calculations of a 19th century French astronomer to the cutting-edge data from space probes, the story of the Roche limit is a testament to human curiosity and our endless drive to decode the cosmos. It shows us that even the most fearsome cosmic forces can leave behind beauty that inspires wonder for generations. As we wrap up, let us take a moment to look upward once more, to the ringed planets in our sky, and see them not just as distant orbs, but as monuments to the power of the Roche limit. The next time you gaze at Saturn's glowing rings, remember, you are looking at a moon that became a masterpiece, torn apart by gravity, to create something far more luminous. The universe is full of such stories, hidden just beyond our sight, waiting for us to uncover them. Please like, comment, share, and subscribe to the channel.